third part, we will main focus on the wormhole induced by the TD bar. Especially in third part, we will main focus on the one-dimensional TD bar deformation. So finally, I will talk about the conclusion and the future purpose. So what is the basic concept of the TD bar deformation? So in this talk, we will main focus on the two-dimensional spacetime with a complex plane. So here is the spatial direction x is denoted by the x, and time direction is denoted by the t. So this is a holomorphic part and also anti-holomorphic part. Now is almost 16 years ago, some logical proposed the such kind of the TD bar deformed operator is like a determinant of the energy moment tensor. So for such kind of the operator expressed by the holomorphic part and the anti-holomorphic part. So in this notation, and we denote the T and as a TZZ component and the T bar marked by the TZZ bar component. So here, normally if we focus on the field theory on the conformal field theory on the flat space, and the theta term will normally will be vanished. So some logical propose that if you can study this for if the theory put on the translation satisfies the translation invariant and also rotation invariant. So such kind of the operator expectation of this operator will satisfy the so-called the factorization property. So this is the original TD bar deformation definition of the TD bar deformation. So we just 5 years ago, and Smolov and Zamlochkov proposed you can put such kind of the TD bar deformation into the original theory. You can start from some so-called seed theory, and you put the TD bar deformation to the original Lagrangian, and after the deformation and the Lagrangian will flow up. So since the deformation parameter with dimension for with energy dimension with a negative energy dimension, so that means the deformation of the TD bar will flow up to the UV. So normally, if for example, if you start from some IR theory and you add the so-called the TD bar deformation, and the energy moment tensor here is generated by the original theory, you can recursively to obtain to flow up this IR theory to the UV. So normally it's hard to solve, but in some special case and special cases, and the effective action can be solved by this so-called flow equation proposed by the Smolov and Zamlochkov 5 years ago. So if you want, once you give a seed theory, for example, here is the S.He or some other kind of the integrable theory, and put the TD bar deformation, and you can automatically use a flow equation to obtain the effective action for the resulting theory. So here one should notice that the energy moment tensor is generated by the original action or original theory. So it's defined by this formula. So it's a very simple philosophy to study this flow equation to obtain the effective action for the TD bar deformed theory. So there is a very simple example. You can start from the so-called free boson theory, and for example, for a simplest case, you just start from the one boson theory, free boson, and you can put the theory on the plane or on the torus. And after the TD bar deformation, you try to solve the flow equation in the previous slides. And after the deformation, you can automatically solve this flow equation to automatically obtain the UV series. So here you start from this IR free series and flow up to the UV. The UV series is that in UV series is a three-dimensional string series. So this is a so-called Lamb-Goto action or so-called long-critical string series. So this is there are some other example to show this. You can exact solve this flow equation to obtain the UV series. So since we know the Lamb-Goto action, there is a string series is a long-local action, long-local series. So in some sense, you can from the local interaction theory, field theory, to finally you can obtain the by TT bar deformation you can obtain some so-called long-local theory. So after in the second part, in the third part we will talk about how long-local interaction induced by the TT bar is also induced. We can generalize the two-dimensional TT bar deformation to the one-dimensional case. So, is there any question for the first part? If no more, we can do we just try to construct the TT bar deformed torus partition function. So we main focus on the TT bar deformed torus partition function. So previously we try to construct the correlation function in the CFT. We put the TT bar deformation to the CFT. The seed series is a CFT. You can start from this. We can start from the CFT and the first order correction to the TT bar deformation to the correlation function is like this. For you just put the TT bar deformation to the original CFT correlation function, and you can since the TT bar deformation satisfies the conformal identity. So you can put this T and the T bar act on the original undeformed CFT, and you can directly to just use this technology to use energy moment tensor conservation to apply the conformal wide identity to extract the first order correction to the TT bar deformed correlation function. So once you apply the conformal wide identity, and after that, finally you just integrate over the full space-time and just to try to do some proper regularization procedure and to obtain the first order correction to the correlation function. So the next part we will go to the higher order. Why this is will be very interesting because up to first order the conformal symmetry is can be approximately to hold, but up to second order the conformal wide identity will be broken down, and so how can we explore the higher order correction to the deformed theory? So we will solve. So particularly we will solve this effective action and also higher order correlation function order by order, just by use perturbation field theory approach. So we start from the TT bar deformation on torus. So basically you put some free boson or free fermion on the torus, and for boson and the undeformed series, the configuration for phi, for example, free boson phi will satisfy the following two boundary condition, and for free fermion, and they are also satisfy the so-called four kind of the boundary condition associated with the mu here is associated with such kind of this number, and one can see that due to the topology of this torus, so we can expect it that so all the correlation function for the free field series are compressed by the double periodical function, for example, Weierstrass elliptic function and also Jacobi data function, for example. And for here is just to give some feeling that, for example, for free theory, and you can see that the 2-point function for this descendant operator associated with a Weierstrass P function and the eta function, and also for the 2-point function, it have a similar double periodical or anti-double periodical function. So we will try to start from, for simplest example, we will try to start from the free theory, and we put the free theory free field theory on the torus. So this is our basic setup, and with our starting point. And our approach is just to try to use a perturbation approach to construct the deformed partition function in Lagrangian partial integral formalism. So here, this is the original phi. We just do the partial integral for the original series theory or deformed theory, and we just deform this. We just deform the Lagrangian by TD bar deformation. So the deformed Lagrangian satisfies the so-called flow equation. We already showed this equation, and we just perturbatively solve this equation to try to extract the partition function on the torus. Here we show some example for in a phase about the free theory of free boson and free formula. So we just start from the deformed TD bar deformed Lagrangian, and we just perturbative the Lagrangian solve this flow equation perturbatively, and the up to first order there is a first order deformation to the Lagrangian, and you have to average over the original Caesar theory. So there are also up to second order. There are some 2-point function of the first order correction to the Lagrangian, and also second order 1-point function associated with second order correction to the partial integral and to the Lagrangian. So this is a standard way to study to construct the TD bar deformed partition function in perturbative quantum field theory approach. So up to this is a first order, and this is a first order and a second order, and we will try to use a perturbative approach, field theory approach, try to construct this such kind of this object. So up to first order, and one can say we start from the free theory. Up to first order, we solve this flow equation by perturbative approach, and the up to the first correction to the Lagrangian is such kind of the partial bar phi square, and up to second order, you can see that there's some so-called higher order derivative return appeared. So up to one can put this guy to the original the 1-point function and the 2-point function, etc. You just because in the free theory we can directly to use a weak construction to construct this expectation value for the 2-point function and the 1-point function, but for this is only for the for the free boson, but for free fermion, and due to the Grassmannian nature and the second order the second order correction to the Lagrangian will be vanished. And also for the higher order, the free fermion will be higher order. The correction to the Lagrangian will be vanished due to the Grassmannian nature. So here we focus on the free boson. So we can do after you put after you work out the 2-point function or the 1-point function, etc., and you have to integrate over this full space-time, for example T2 and double integral and also associated ones one integral. You have to regularize the second order correction to the path integral. So for the free boson and free fermion, we already in this paper we construct this already construct this so-called counter term to cancel all the divergent piece in this perturbative calculation, and all this but if once you there is one more comment is that if you consider higher order, you have to, due to the TD bar deformation is a long in perturbative sense, it's a non-realizable theory. So you have to introduce additional higher order counter term appear here. So to cancel this so-called the divergent piece. So once we introduce here, we just use the free minimal subtraction to regularize the partition function. So finally, we will see what will happen. So for the free boson and the zeros the free boson on deformed theory, the partition function is look like this. And for the first order and the second order, the additional term, since the free boson, the additional terms appeared due to the second order correction to the Lagrangian. So the final resulting series for the fourth order, we just use a minimal subtraction to obtain the by the Lagrangian formalism, and we obtained this formula is consistent with the Harmony, Shuvik, and and other people just given by the 3 years ago. They use a different approach, try to solve this progress equation to exactly use a so-called Hamiltonian formalism to construct the partition function in non-perturbative way. This is a perturbative result is consistent with their result, but we use a Lagrangian formalism. And up to second order, due to these additional terms, there are some terms appeared. And the first term is consistent with this result given by this paper, and how to deal with this additional terms. Additional terms is we have to due to the 2-point function for the phi for free boson and the torus, and we have to take care of this so-called the contact term. This here appeared. So once you consider this contact term there and the second order correction to the Lagrangian 1-point function contribution to the second order partition function will automatically cancelled. So finally, this additional term will cancelled. So we are very happy to so our Lagrangian formalism consistent with the Hamiltonian formalism finally. So this is for the free boson, and also free fermion. Free fermion due to the second order correction, this law will be due to the Grassmannian nature. So this term will be automatically vanished. So that means the free boson automatically satisfy this consistent with the Hamiltonian formalism result. So is there any question about this okay, let's move on. So next we will talk about the so-called the KdV charge operator. And for generically we can put in a Lagrangian theory, and we can put any primary operator or maybe some others local or non-local operator here. And we put this put operator here with a flow effect, because since we already consider we do the TD bar deformation, the Lagrangian will deform and also the operator will be deformed. The deformation will also satisfy so-called flow equation, consistent with the flow equation. So up to the first order, there is a first order deformation and undeformed series, or even for the operator, primary operator in the safety or some descendant or something like that. So this is a first order correction. They are associated with these three terms, and we just solve the flow equation for this operator. We put these answers like the lambda here is associated with the deformation parameter, and you can put this operator into the flow equation and solve it order by order. Then finally, we can obtain the correlation one-point function, for example, T lambda. But since the KdV operator is defined by this the integral over from holomorphic part from 0 to L to capital L. So this is associated with energy moment tensor up to some power. So we can do the simplest example. So for example, we consider the small s equal to 0 case, and we can finally we just put this guy into this to just use in free field theory, and we can use a weak contraction to construct this correlation, a one-point function, and etc. And this one-point function for the first order correction to the Lagrangian we already obtained. So we just have to work out this term and this term. So finally, we can obtain this result is associated with eta function and also derivative of the eta function. So this is consistent with this recent paper where abstract given by last year, and this paper is given by just construct the KdV charge operator, expectation value of the KdV charge operator, and try to use a non-perturbative way to just try to solve the Borges-like equation to obtain the so-called wave of the KdV charge operator. Finally, we find that our result is consistent with their result. So this is the so-called the KdV charge operator. So is there any further question about this? Okay. If no more, we will move to the one-dimensional TD bar generalize the extend of the TD or two-dimensional TD bar deformation to the one-dimensional case, and we will see how the wormhole structure induced by the one-dimensional TD bar deformation. So we basically in two-dimensional case, the TD bar deformation can be regarded as you can start from some so-called seed series is lived on here, and the seed series once you introduce a TD bar deformation, there is an alternative point of view to consider the TD bar deformation. So you put a seed series here, and the seed series coupled with so-called two-dimensional massive gravity. So the gravity is parameterized by this Weber field, and also the G mu mu here is so-called the dynamic field, and the gamma mu mu is associated with the reference field. Reference background, and once you in this paper, and Tony and shows that this you just solve use this default the seed series coupled with massive gravity. You just use equation of motion for the F mu reference Weber, and you can define the energy moment tensor for the deformed series. And you can also you can also use dynamic variation of the dynamic variant, and you can obtain the original energy moment tensor of the undeformed series. And here you have to use the so-called equation of motion for so-called the equation. So here E star is associated with the solution of the equation of motion of the E mu here. So you can put this solution, you can put this solution to back to the massive gravity to back to the S lambda is a so-called the city series in coupled with massive gravity. You can here you can do the derivative of the with respect to lambda and use and also combine with the equation of motion for the dynamic background. And finally, you can obtain up to the use this unshared value of the gravity, and you can find that the resulting series satisfies the so-called the flow equation. So this flow equation is in the classical level is same as the TD bar flow equation. So this is a two-dimensional story. And how about the one-dimensional case? We can use this similar technology to extend to the one-dimensional case. One-dimensional case, we just we put some Hamiltonian system or some one-dimensional field series system coupled with one-dimensional so-called one time. Here we call the one-dimensional massive gravity. So E mu here is associated with the dynamic Weber field, and also reference V mu is associated with reference field. And we can solve this equation of motion for the E mu and also respect to the V mu. Here we choose a purple dynamic field. We can construct the so-called the equation of motion or flow equation. Here, for particularly we can start from the so-called SYK model, and we put the Hamiltonian since the David Gross and his collaborator already constructed the one-dimensional SYK TD bar deformation, and they constructed the Hamiltonian something like this. And here because the one-dimensional massive gravity is we do not know the exact form for the one-dimensional massive gravity, and so we have to work out the capital B here is associated with the massive gravity action for the in one-dimensional case, and we just use we just try to reproduce the David Gross result, and we finally obtain this one-dimensional massive gravity. So once you obtain the one-dimensional massive gravity, you can use the autological approach to try to construct a one-dimensional generic one-dimensional TD bar deformation. Here there because there is just only simple one single SYK model, and we try to construct a multiple Hamiltonian system to couple with the one-dimensional massive gravity to construct a generic TD bar deformed Hamiltonian system. And so use this technology, and we can start from the, for example, we can start from the single the two decoupled Hamiltonian system. The Hamiltonian is denoted by the left hand part and the right hand part. The originally the two Hamiltonian doesn't talk with each other, but we can use our technology to couple with a one-dimensional massive gravity, and to try to construct the TD bar deformed the Hamiltonian system. And finally we get the Lagrangian or Hamiltonian, like something like this. Generally, you can put some Lagrangian series, one-dimensional Lagrangian series, and doesn't talk with each other. And after the TD bar one-dimensional TD bar deformation, and you can finally get a resulting Lagrangian. So this is a very simple exercise. One can show that after the TD bar deformation and the left hand, the two disentangled part will finally become entangled. So here we can start. Just for the simple exercise, we can start from the two Hamiltonian system, and after the TD bar deformation, and since the TD bar deformation is nonlinear, here we can productively solve this TD bar deformation. Up to fourth order, we can see we start from the single. We start from the two Hamiltonian system, and we expand to the up to fourth order. And because this is a TD bar deformed theory, we will have to construct the originally we can construct the TD bar deformed so-called the thermal field double state. And see here, the bracket is associated with eigenvalue for the left hand side and the right hand side. So the energy momentum. So here we just put the eigenvalue of the eigenvalue is associated with the TD bar deformed Hamiltonian. And after your preparation of the TD bar deformed thermal field double state, and we just do the normalization in proper way, and we can construct this so-called the TD bar deformed TFT. So up to fourth order, we want to try to see the entangle between the left and the right. So you can put some in disentangled operator, something like this. So this is a left operator associated with left Hamiltonian, and this is associated with right hand operator associated with right Hamiltonian. So there is the good sign to see the non-local TD bar deformation as a non-local, or try to TD bar deformation will induce the wormhole. You have to consider the deformed retarded correlator defined by this we just put the left and right the bracket of this the commutator of this. Originally, if the series does not talk with each other, and because the left and right hand operator does not entangle, so they are commuted. So you can study this object, and up to the 4 lambda in the undeformed series, they automatically will be vanished. So, but we can prepare we can average this bracket, this commutator in the TD bar deformed CFT, and you can study this. You can productively to study this correlation function up to fourth order, and you can here we show some up to fourth order where we show some numerical result. So normally for the deformed retarded correlation function is associated with the real part is associated with statistical correlation, but for the imaginary part was there's some associated with the quantum entangle between the left and the right. So here we put some signature in the right hand side in the T minus beta here, and T minus beta here. So the T1 this is time in the left hand side, and this is associated with time in the right-hand side. So you put a t here, beta t left goes to beta, and you can see that from this picture shows that once you can put a circular in the right-hand side in the beta and the beta minus beta, and after the time evolution, the t equal to beta, and the right-hand side will get the signal from the left-hand side. So basically, that shows that this figure shows that shows that once you can send from the from the left-hand side, you send a signal here, and after the time evolution, and you can automatically you can obtain the maximum signal in the right-hand side. So that means originally the two series does not talk with each other, but after with TT bar deformation and with the TT bar deformation and the two sides will talk with each other. In some sense, it's a so-called it's some non-local effect induced by the TT bar deformation. This is a very strong signal to see that after the TT bar deformation and the so-called wormhole. Here we just call the wormhole, not just studied by study the retarded correlator here. So is there any question about this situation? Okay, let's summary. So in this talk, we just constructed the second order correlation, which will consider the TT bar flow effect on the operator and also on the Lagrangian in path integral formalism. And also we already studied the KdV the wave of the KdV charge operator in the deformed TT bar deformed theory, and also we formalized the one-dimensional TT bar deformation to realize a quantum transversable wormhole in multiple TT bar in multiple Hamiltonian system, and so there are some future problems that you can generically to consider the higher order correlation function with a TT bar deformation, and you can also consider the higher order correction and also higher genus Riemann surface, two-dimensional Riemann surface with a TT bar deformation, and you can previously we just only consider the field theory TT bar deformation, and also since two-dimensional for example, two-dimensional gravity does not in normal sense is not a realistic gravity. You can do the similar sense for the JT gravity, for example, plus safety. In some sense, JT gravity plus safety is can be identified, in classical sense can be identified the JT safety with TT bar deformation. So in some sense, you can use the TT bar deformation, try to construct the correlation function for the so-called the JT plus safety system. And in this setup, you can study so-called the black hole information paradox, and also you can consider the because many there are in a two-dimensional bosonization structure, for example, fermion and boson, there are have some so-called bosonization duality, and you can how about the bosonization commuted with TT bar deformation? You can do the TT bar deformation to the two-dimensional theory and to see what will happen to check polarization structures still hold a lot. And also you can use our current approach to try to construct the correlation function in the Lorentz-Bricken theory. And okay, that's finally we can also consider the generic TD bar deformation for the two-dimensional gravity or etc. Okay, thank you for your attention. Yeah.
Okay.
So I have time. Yeah.
Yes. Thank you. Let's thank the speaker. And comments, if there are any questions or comments for. Okay. Okay. If there are no questions or comments, let's thank the speaker again.
Thank you.
And, we